This is electronic devices, and we're going to do a review before we continue with new material. So, that being the case, we can have things that are in series. Now, series means one right after the other. So I got one thing, I got another thing, I got a third thing. So, and because this is an electronic class, I could have things like resistors. We didn't cover it during the syllabus, but all phones are going to be left on during class, so that in case you get an important message. And we can have capacitors, and we can have inductors, and if I have a resistor, then it has some resistance that's in ohms. And if I have a capacitor, it has capacitance reactance that's in ohms. And if I have an inductor, I have inductive reactance, which is in ohms. So all those things are in ohms. If I have a resistor, then my resistance is on the real axis and is in ohms. If I have inductive reactance, then I'm on the imaginary axis in the positive direction and I'm in ohms. If I have capacitive reactance, I'm on the negative direction on the imaginary axis, and again I am in ohms. My reactance, inductive reactance, is going to be 2 pi FL, where L is my inductance, which is in Henry. If I could spell Henry. And my capacitive reactance is going to be 1 over 2 pi FC, and my capacitance C is in farads. Alright, so that being the case, if I have 3 resistors that are in series, R1, R2, R3, then my total resistance is going to be R1 plus R2 plus R3, also known as the summation of the resistances. We could write it that way too. If I have inductance L, so I've got 3 inductors in series, 1, 2, 3, and I've got L1, L2, L3, then my total inductance is going to be L1 plus L2 plus L3, plus or minus the mutual inductance, right? So normally we ignore the mutual inductance and we don't add that in, but there might be mutual inductance going back between those guys, and we'd have to compensate for that. But this is just a review, so we'll ignore that situation for right now. If I have capacitors that are in series, so I got capacitor 1, capacitor 2, capacitor 3. These guys are all in farads. But then my total capacitance is going to be 1 over the capacitance of 1, plus 1 over the capacitance of 2, plus 1 over the capacitance of 3. And hopefully you'll get to the point where your calculator does that for you very expeditiously, and it's not a real problem. Right. Okay. If I am in parallel, did I spell parallel right? I don't know. I might. So now I have something in parallel. So I've got a resistor, another resistor, and a third resistor. So I got R1, R2, R3. The total resistance is R1 in parallel with R2 in parallel with R3. So that'd be shorthand of writing that notation, but that won't do me much in my calculator. Is also 1 over R1 plus 1 over R2 plus 1 over R3. So if I have capacitors, I have 10 ohms, and I have 20 ohms, and I have 30 ohms. If I had that, I want to know the total capacitance. I could say, well, that's 1 over 10 plus 1 over 20. Who's writing up here anyway? Somebody messed that up. 1 over 20 plus 1 over 30. And then we could go and find a common denominator, invert and multiply and do all that thing. But that's not what we do. What we do is we use our calculator and we go 10, the 1 over key, plus 20, the 1 over key, plus 30, the 1 over key. And you'd have to find where that key is, equals 1 over key. And that's going to give you the answer directly, and you wouldn't be finding a common denominator, you wouldn't be inverting and multiplying, you wouldn't be doing any of that other stupid stuff. You would just be using your calculator to get the right answer. If you have a graphing calculator or my TI-36 Pro, I would probably just enter it as you see there. I'd probably just enter 1 divided by parentheses. 1 divided by 10 plus 1 divided by 20 plus 1 divided by 30, close parentheses. And the calculator would give you the right answer right off the bat. Now, if I'm in series, my total resistance has to be bigger than any of the individual resistors. If I'm in parallel, my total resistance has to be less than the smallest resistor. So in this particular example, I have 10, 20, 30. If I don't get an answer of 7 or 8 or somewhere less than 10, I know my answer is wrong. Okay, so now I'm going to take my calculator and all right, so there's my calculator, and my calculator is okay. Can you read it? Maybe you can't. And we'll clear it. Oh, I can see it just fine here on my screen. And so I'm going to go 1 divided by parentheses 1 divided by 10 plus, where's plus key? 1 divided by 20 plus 1 divided by 30. Do I have that in right? Enter. And it's going to tell me it's 5.4. So it's going to be 5.45 ohms. And then we'd have to ask the important question, which is, how many significant digits can I keep? You know, I have 10, I have 20, I have 30. These guys are all plus or minus 10 guys. I'm not going to be able to keep 3 decimal points. So for a final answer to such a question, I would probably say 5 ohms, because I only have 1 significant digit. Now, this particular new calculator doesn't have the 1 over key some of the other guys do, so, but I like the 1 over key on the other calculator better. Okay, so now, where was I? Anybody know where I was? All right, we're in parallel. Okay, well now, if I'm parallel and I have capacitance, C1, C2, C3, then my total capacitance is going to add C1 plus C2 plus C3. If I have inductors in parallel, Then assuming that I don't have any mutual inductance, which would hose me over, I've got L1, L2, L3. Now my total inductance is going to be 1 over L1 plus 1 over L2 plus 1 over L3. So that's how I would do that. Okay, so now Kirchhoff, Kirchhoff, not even close. Kirchhoff comes around. Everything was fine. We had Henrys, we had farads. Those are normal continental things from the English, from the French. Everything's fine. We have volts, we have amps. Those are French, those are Italian. Everything's fine. Now the Russians come in, Kirchhoff, and Kirchhoff says that if I take the summation of the voltages around some loop, I'm going to get 0. And if I take the summation of the currents going into some node, I'm going to get 0. So that's Kirchhoff's law, voltage law, Kirchhoff's node law. And so if I have some circuit, I got resistor, and I got a battery sitting there. And this is 10 volts, and I got 10 ohms and 20 ohms and 30 ohms, something like that. Then there's a guy by the name of Ohm's law that comes in, and Ohm's law says V is equal to IR. Voltage has to be current times resistance. So I already found the total current, the total resistance, 5.45 ohms. Now I told you that as a final answer I only had one significant digit, but if I'm going to calculate something, I'm going to carry more significant digits in my calculation. It's only when I have the final answer do I worry about significant digits. So I know the resistance total, I know the voltage, so the current through this circuit is going to have to be the voltage divided by the resistance, 10 volts divided by 5.4 ohms. So I got some current, yeah?
Your RT isn't right.
It's not right?
And we were in a series, that'd be if it was in parallel.
Oh, yes. Thank you very much. I was just checking the class, see if anybody catch that. 60, and now 60, so that'd be 1/6 of an amp. And we could leave it that way, or we could take our calculator and say 1/6 of an amp is what? 170 milliamps. Currently my calculator is set to only show 2 decimal points. So if it wasn't, it would have come up 0.66, but then I would have rounded it up to 170 milliamps anyway. Well, now that I know the total current, I know the voltage through the 10 ohm resistor, and I know the voltage through the 20 ohm resistor, and I know the voltage through the 30 ohm resistor. How do I know that? Well, voltage is current, 170 milliamps, because in series, every single one will be the same, milliamps. Wish I could spell milli better. Times the resistance, 10 ohms, times the resistance, 20 ohms, times the resistance, 30 ohms. 1.7 volts. 3.4 volts. 5.1, 5.1 volt. Now, this, if I add this together, I should get 10, right? I should get 10 volts. 5, 6, 7, 8, 9, 10. I get 10.2. How come I get 10.2? Well, because I rounded at 170 milliamps. If I would have kept it 166, I would have gotten closer to 10 when I added them together. But I'm only going to keep 2 significant digits anyway, so I'm probably not going to change that any. Okay, so now we're going to do something different. What do I want to do different? All right, we got some AC circuit. I got 120 hertz, and I've got 120 volts. Why not? That's bad. Why don't we have 10 volts? And I've got an inductor, and I got a capacitor, and I have a resistor. Let's see, we got 10 ohms there is my resistance. My inductance going to be, why don't we have it be 50 millihenry. That looks good. And then my capacitance, we're going to go with 1 microfarad, just to have something to go with. All right, so the first thing we're going to want to do is know what the inductive reactance is. X of C, X of L, 2 pi F L, 2 pi 120.05. All right, so I take my calculator, 2 times pi times 120 times 0.05, and I get 37.7 ohms, and it has associated with it an angle of 90 degrees because it's going to be in the positive imaginary number direction. Then I'm going to calculate my X of C, which is going to be 1 over 2 pi FC, 1 over 2 pi 120, 1 microfarad. Okay, so 1 divided by parentheses 2 times pi times 120 times 1 exponent minus 6. Wow, I got, that's not going to work. Let's make it, instead of 1 microfarad, let's make it 10, we'll make it 100 microfarads. Okay, so now we're gonna do the calculation again with 100 microfarads, and we're going to end up with an answer of 13.26 ohms, and it's going to have a direction of minus 90 degrees. Okay, so now that we've done that, we need, when we have AC circuits, we have impedance. So my total impedance is going to be the square root of the real component squared plus, which is the resistance, plus X of C, X of L minus X of C squared. So I've got some resistance going in the real direction. I got some X of C going that way. I got some X of L going that way, X of C going that way. Those two are going to cancel each other out to some effect, and I'm going to have a vector going this way. I'm looking for that angle. I'm looking for that magnitude and that angle right there for my impedance. So that's the whole purpose of what I'm doing. All right, so I come back up here and I say, well, impedance total square root of 10 ohms squared plus. And it doesn't matter who's being subtracted from whom, because I'm going to end up squaring it. It's going to be positive anyway, right? So I'm going to have 37.7 minus 13.26 squared. And I'm going to be going the other way in case anybody was wondering. So really I'm going that way, not that way, because the x of c guy 1 is base. Square root of 100 plus 24.4 squared. All right, ready for my calculator. Square root of, where's my square root key? That's square root of 100 plus 24.4 squared. Boom. So I get 26.4 ohms at some angle. Now I have to get the angle out. Alright, so what I'm going to do, because it's this calculator and not my other calculator, I'm going to do something different for you. Okay, so in my mode, I have my calculator set for magnitude angle. Okay, so that's what I have in my mode. I'm going to click my mode, and I'm going to put in 100 plus 24.4 I. And there's a key here with a pi on it, an E on it, and an I on it. And so what I've done is I put in my calculator the imaginary number associated with the problem I'm doing. Because my calculator is in polar mode, when I hit the enter button, it's going to tell me that my answer is wrong because I entered it wrong. So I'll do it again. 10 plus 24 plus 4 I. Boom. So I have 26.4, the same number I had before, but my angle is 37.7 degrees, 67.7 degrees. Now, I can see that extremely well on my monitor. Can you guys see that okay? Yeah, you see that okay. So, with this calculator, I didn't have to do any trig, I didn't have to do other things. Okay, now, with the TI-36 that isn't the Pro, what you would do is something different. Okay, so, with this calculator here, with the graphic calculator, you're just going to put in the value you want. Put in the number that's going to tell you the answer. But on this calculator, what I need to do is I need to put in the 10. Well, I'm going to clear it first. 10, the XY key, which is right there. And then I'm going to put in 24.4. I'm going to hit the equal button. And then there's a rectangular to polar conversion key on the bottom. Third function, rectangular to polar. I come up with 26.4 again, same I got last time. I hit the XY key and I see the angle is 67.7, the same angle that I had. So with the TI-36, what I'm doing is I'm doing a polar rectangular conversion using my polar rectangular conversion. So that's pretty relatively cool. And with a little bit of luck, Annette will explain all that stuff to you in Tech Math, and it'll be perfectly unclear when she's done. No, it'll be perfectly clear when she's done, right? Whatever. And then in Tech Math 3, I'll just do it again. So right now, all the blank looks I'm getting are great. That's wonderful. Don't worry about it. We go over enough times, it'll be okay. What do I need to do next? Oh, once I get the total impedance, I can find the total current. So the total current is going to be the voltage divided by that impedance. Oh, we got to change over? Yeah. Okay, we're back?
Yeah.
Okay, so my voltage was 10 volts. My impedance was 26.4 angle 67.6 degrees. Okay, so my current's going to be 10 divided by 26.4, which is, we'll call it 380 milliamps at an angle of minus 67.7 degrees. When I'm dividing by some angle, that angle becomes negative when I put it up on top. So if I had 1 over x squared, I could write that as x to the minus 2. That would be the same type of thing, because the polar representation of a vector angle, magnitude angle, is the same as e to the j theta, and that makes it an exponent. So I'm using it as an exponent thing when I have it underneath. All right. So now I know the total current. With the total current, I can now find the voltage across the inductor, the voltage across the capacitor, the voltage across the resistor. So that's what I'm going to do next. So voltage across the resistor would be the current, 380 milliamps, angle minus 67.7, times the resistor, which was 10 ohms, right? And the voltage across the inductor would be the total current, 380 milliamps, angle minus 67.7, times the inductive reactance, which is 27.7 angle 90. 37.7 angle 90 degrees. And then the voltage across the capacitor would be 380 milliamps, angle minus 67.7, times the capacitive reactance, 13.3 angle minus 90. All right, now I throw those guys in my calculator and I'd end up with answers. So I'd 3.8 volts, angle minus 67.7 degrees. Can't do this one in my head. .3 volts, angle 22.3. Oh, we have days like that, don't we? And voltage across the capacitor, 5.1. angle minus 157.7. So I'm adding the angles together because I'm multiplying, and I'm multiplying the magnitudes together because I'm multiplying. Okay, and a show of hands, how many think I'm right? Well, there are 2 believers in the group. What more? What more can I want, right? So now we should come up with some proof, right? So no, we shouldn't. Somewhere on this machine, I think I have I used to. Don't I have the Mollison program on this machine? I did last? Yeah, where is it? Come, I don't see it. Oh, there it is, right there in plain sight. So this is a simulation language we use to fake circuits when it's time to do it. Well, when it comes to the point where the math is going to be too hard, we just put it in the circuit and measure. Okay, so we're going to have to remember what the circuit is. So 120 hertz, 10, 50, 110. Okay, I got it memorized now. Thank you very much. I'm going to need a ground, so I'll get a ground. The ground is for simulation purposes. I need an AC power supply. I'm going to need a resistor. The resistor is down here, right? And I need an inductor. The capacitor is over there. And I need an inductor. It doesn't matter what order these guys are in. They're in series, so it shouldn't be a problem. And I have 10 volts. I got 120 hertz. I got 10 ohms. Got 50 millihenry. And I have 100 micro. Can't get the Greek letter in, so. All right. We'd sort of like to rotate this guy a little bit. All right, well, don't rotate. I don't care. Whatever you do. I don't care if you rotate or not. Why am I not rotating? Oh, I'm pushing the wrong button. All right. Can't have everything. All right, now get rid of that guy for a moment. See if I can hook up some wires. Now, do I need to put voltmeters on everything for you to believe? Probably, right? All right. So I'm going to come get some voltmeters. So there's a voltmeter. And that's not the one I want. I'll put it over here. Voltmeter there. I want a horizontal voltmeter. Put one there. Put one over here. And we'll throw in an ammeter. Throw in an ammeter over there. Alright, so now we got enough. Now we can measure everything that we were supposed to have measured to see if it's right. And if I were going to do this problem, I would probably build it first and tell you what the answers was first, and then worry about other things second. Okay. So we anybody going to tell me what I did wrong? No one's going to tell me what I did wrong? I got up this morning. It's an AC circuit. All the instrumentation is DC. Of course, it isn't going to work. But you knew that, right? You were going to tell me that. Yeah, you're just holding back. You just didn't want to be smart. Yeah, make sure I knew before you told me. Yeah, I understand that. That's perfectly, it makes perfect sense to me. Yeah, on your final exam yesterday, last time I did that to you, I had a DC voltmeter in one of those problems, and it shouldn't have been. Okay, so 380 milliamps, that looks right. 14.3 volts, is that what that's supposed to be? 5.5, that's what that's supposed to be. Was that supposed to be like 38? 3.8? Are those the right answers? Do we remember?
Yes.
I think, yeah, I think
They are.
within some significant digit, yeah. Now the issue is, how am I going to get the angle? And that would be a more difficult thing to do in multi-sim, but it is something that we could do if we wanted to. Yeah, put the oscilloscope on it and measure what the angles are. Yeah, exactly. So you want me to do that too? Or is that too boring? So if I take an oscilloscope, 4-channel oscilloscope. Oh, okay. And we'll hook one on this guy and one on how am I going to do this? Yeah, all I'm going to do is make myself look like a complete idiot by not being able to do it, so I'm not going to. How's that? Is that good? With your lab book open to the right page, you can do that, right? And with your lab book not open to the right page, you probably won't be able to do that. If I would have put the resistor on top and the inductor on the bottom, I would have had a chance. All right, well, let's go back to something easier. I have a battery, and I have a resistor, and I have 10 volts there, and I have 10 ohms here, and I have 1 amp flowing in the circuit. The issue is the current going that way, or is the current going this way? Which way is the current flowing? And that seems like a fundamental thing, right? Anybody want to tell me black or purple? Okay, so you have two choices. You can tell me black or purple, or the question is hosed, you're doing it to us again. So you have three choices: black, purple, the question's hosed. All right, so we'll vote. We vote on these things. So, all right, so we're going to vote on black, vote on purple, and we'll vote on hosed. All right, how many for black? 1, 2, 3, 4, 5, 6, 7, 8, 9, 10 for black. How many for purple? How many for the question's hosed? How many for, oh, okay, so two are going to vote for hosed, 2 for hosed, nobody for purple. All right, so the correct response is hosed. Your book is a conventional flow book. So your book is conventional current flow. Conventional current flow is black. Okay, so those that answered black are just answering what I taught you last semester. Black, conventional current. Current flows from the positive side to the negative side of the battery. But those of you who are Navy trained, like myself, know that for electricity to flow, what's flowing are electrons. Electrons are negatively charged, therefore the current has to leave the negative side of the battery and flow to the positive side of the battery. So the Air Force answer would be in black, but the Navy answer would be in purple, and the book's answer, because it's conventional current flow, would be in black, But the same author has another book that's electron current flow, and it's going to be the purple guy. And in fact, when we start chapter 17 and I bring up the transparencies provided by the author, they're all going to be electron current transparencies. Every single one of them, I'm going to have to change the polarities on them to be different. All right, so in the big picture of world things, who gets to decide which way current flows? The Air Force, the Navy, or neither? Neither. Okay, so the guys that decide, that make the decision which way current is flowing is IEEE. Those are the guys that get to decide. The International Electrical and Electrical Mechanical Engineers, about 500,000 of them, and they get to decide. And if you look, if I take my wallet out and pass out all the money that's in it, you will finally get down to my IEEE membership card, which says I've been an IEEE membership for 18 years. Is that what it says? Yeah, for the last 18 years, I've been paying the school has been paying for me my IEEE dues. Those are the guys that decide whether whether current flows from the positive side of the battery or if it flows from the negative side of the battery. And they've decided that current will flow from the positive side of the battery, even though every single physicist in the world will tell you no proton moves, and in order for that to happen, you have positive holes flowing in your wire, and those holes are filled up by the electrons going the other way.
What about positive ground on old equipment?
Yeah, the old equipment would have a positive ground on it. Yeah, exactly. So, so when Edison was doing the electrification of New York City, before Westinghouse decided to go with AC power, he did it, and he had positive grounds. He most certainly did. Okay. So so now in this chapter, in chapter 17, we have our first symbol is a diode, and because IEEE made the diode, the current's flowing this way into the funnel and out. We don't look at it as negative current flow trying to get going the other way. We don't look at it like that. So that's just the way that is. Okay, is it time for lunch? Is that what you're trying to tell me? Let me check the syllabus. It's 30 seconds here to see whether or not I need to do another review. Oh yeah, I got the next 2 hours to do the review. For the new people in the room, I have a color chart that we printed out last semester to do on the final exam. So for the new people, if you want to take them with you. Okay, thank you very much. See you soon.
I'm new.